Hello everyone and welcome to the first MDPI webinar on nanomaterials, which is entitled Advanced Mechanical Modeling of Nanomaterials and Nanostructures. Thank you very much for joining us today. This is the first webinar of a series based on special issues and sections from our Nanomaterials journal. If you wish to submit your paper to a special issue related to this topic, please check the webinar's website. Our chair today is Dr. Francesco Tornabene from the University of Salento in Italy. We will also have two speakers, Dr. Rossana Dimitri, also from the University of Salento, and Dr. Salvatore Brischetto from Politecnico di Torino, Italy. After both presentations, we will have a Q&A session during which we will address some of the questions submitted by you, live online audience. So if you're joining us live, please start thinking of some questions now and submit them at any time during the webinar. You have to submit them on the Q&A box, which is very important, not in the chat. And as we have more than one speaker today, please address your question. So mention the speaker to which you are submitting the question. Mention the name together with your question. So I would like to remind everyone that this webinar is being recorded and that the recording will be available soon at the webinar's webpage. Now I'd like to introduce our chair. Dr. Francesco Tornabene received his PhD in instructional mechanics in 2007 from the University of Bologna. In 2011, he became a junior researcher within the research program entitled Advanced Numerical Schemes for Anisotropic Materials. Then he was an assistant professor and lecturer at the Alma Mater Studiorium of the University of Bologna. From 2018 up to date, he is an assistant professor in instructional mechanics and lecturer at the Department of Innovation Engineering at the University of Salento. His scientific interests include the structural mechanics, solid mechanics, innovative and smart materials, computational mechanics and numerical techniques, damage and fracture mechanics. He's author of more than 260 scientific publications and 11 books, and collaborates with many national and international researchers and professors all over the world. He's also an editor-in-chief and a member of the editorial board of numerous international journals. In the last years, he received different important awards, such as the highly cited researcher by Clarivate Analytics, Ambassador of Bologna Award, and member of the European Academy of Science. So now I hand over the floor to Dr. Tornabene and enjoy the webinar.
Thank you very much, Elena. And I will start sharing my screen. Thank you very much to all the participants to be here. It's a pleasure for me to be here to present our first webinar. And I want to thank MDPI company to give me the possibility to chair this webinar. And then I will start giving you some information about this webinar, because this webinar is related to a special issue that I and Professor Dimitri have organized in nanomaterial journals, and entitled Advanced Mechanical Modeling of Nanomaterials and Nanostructures. If you want to submit some paper, the submission are already open, and you can submit a paper about within April 23, 2021. And here I have reported some of the papers. At the moment, 6 papers we have published in this special issue. And other papers are under review, and some other colleagues have promised that we will submit some other papers. So, and regarding the webinar, I want to spend some words. In line with the interest of the special issue, Advanced Mechanical Modeling of Nanomaterial and Nanostructures, the present webinar will focus on theoretical and numerical modeling of heterogeneous material and enhanced structures, whose response could be affected by stacking sequence, ply orientation, agglomeration of nanoparticle, volume fraction of the constituents, and porosity level. The series of talk will show different results for large numerical campaign, focus on fiber-reinforced composite laminates, functionally graded materials, carbon nanotubes, graphene nanoplatelets, augmented materials, latticeal and cellular honeycomb materials, smart constituents, together with innovative and advanced classes of composites such as variable angle toe laminates. Among many possible structural applications, composite beam and shells with different geometry will be discussed due to their unique shapes and outstanding mechanical behavior, accounting for their possible size dependence. In the contexts where an increased computational demand is required to solve such complicated solid mechanic problems, the webinar discusses about different higher performing computational strategies and advanced theoretical formulation, which are evaluated systematically against the available literature in their reliability and accuracy. So this is today we will start with the first event, first webinar, October 16. But we have another event, and I want to highlight on October 30. And this is the program for today. And after my introduction, I will give we will have the presentation of Professor Dimitri, and after that we will have the talk of the second speaker, Professor Brischetto, and finally we will have a moment for discussion. And so I will start for the first speaker, Professor Dimitri. Professor Dimitri is an associate professor at School of Engineering at Department of Innovation Engineering, University of Salento. He won a PhD award in 2013 in ECOMAS event, in particular for computational mechanics GIMC in the Italian section. He worked in Gottfried Wilhelm Leibniz University in Hanover, and he worked also in ERC, starting the research grant called the Interface on Computational Mechanics Modeling of Structural Interface based on isogeometric approaches. She is author of more than 100 scientific publications. She collaborates with many national, international researchers and professors worldwide, and she also collaborates with different prestigious international journals in the structural mechanics fields as a reviewer, member of the editorial board, and guest editor of this special issue. So the title of her talk is High-Performing Numerical Method for the Mechanical Study of Nanocomposite Material and Structure. So please, Professor Dimitri, you can start. I stop sharing my screen, and please share your screen. Thank you very much.
So good morning, everyone. With the present talk, I want to show you some theoretical and numerical models to treat heterogeneous materials and structures, focusing in particular on two-shell structures, whose response could be affected by many factors, let me say stacking sequences, prior orientations, volume fracture of the constituents, and so on. So after a brief introduction, I will show you the main basics for anisotropic laminated and lattice shells. Then I propose you the so-called generalized differential quadrature and generalized integral quadrature methods as efficient numerical tools to solve different structural problems, while we apply different materials and constitutive relations within a large numerical investigation. So here I briefly describe the three basic aspects of the problem. I mean, the first two theoretical ones based on a unified formulation and the differential geometry for a general description of higher order physical shell theories. And the last one has a computational nature and relies on the two numerical techniques here applied to approximate the derivatives and the integrals of equations involved in each selected problem to check for accurate solutions. So these are the GDQ and the GIQ respectively. So more theoretical and computational details about materials and the structures here presented can be found in these books, and where you could recompute, let me say, all the results with the free software. Here you can see the name of the software that you must have written during the years. So let's start with the theory of anisotropic laminated shells, whose general shape is defined by means of a reference surface, curvilinear coordinates, and with the position vector for an arbitrary point of the solid throughout the thickness, which is in turn defined by means of the position vector of the corresponding point on the reference surface. So in a differential geometry context, this corresponds to introduce the metric of the parametric curves and surfaces by means of the first fundamental form and the Lamy parameters. And then we will define the curvatures with the second fundamental form and the normal vector definition of each arbitrary point of the shell element. So in a principal system of coordinates, this means that the quantities f and m will be equal to 0, where the principal radii of curvature are defined through these ratios you can see here below, R1 and R2. So briefly, I introduced the kinematic model within a unified formulation that allows to study and compare several higher order displacement fields in a unified manner, such that the mechanical behavior of doubly curved structures is defined by proper selection and choice of several thickness functions that characterize the kinematic expansion along the three principal coordinates. So in this context, we defined a moderately thick shell according to an equivalent single layer approach, including the zigzag effect or Murakami function, as you can see here in the extended form. Here you see an example of higher order shear deformation theory depending on 18 degrees of freedom, where the well-known Risen and Mindrin theorem in the first order shear deformation theory represents just a subcase defined by means of two thickness functions and 5 degrees of freedom. So look at the reduced kinematic relation here below. And due to the general assumptions of this approach, each thickness function can take a different expression, you see here. And according to this choice, several kinematic models can be obtained and studied. So now for simplification purposes, we can define generally the kinematic model for an equivalent single layer approach in this kind of compact form where we account for the zigzag function and Murakami function. And look at the following different unified formulation examples. As first example, if a fourth order kinematic expansion is considered, we obtain this following higher order kinematic model where we use as thickness functions the power series, or assuming different thickness functions such as hyperbolic, sine and cosine, that yields the following kinematic models here below. And based on the compact notation, several structural theories characterized by a different order of kinematic expansion tau can be obtained for thickness functions independent of the principal direction for each generalized displacement components. And here you can see this kind of list. Starting with the kinematic assumptions, we can define the kinematic equations for doubly curved shell structures, which relate the strain components and the kinematic field by means of a kinematic differential operator that can be redefined. So here, as you can see here, within an equivalent single layer approach. So where the following definitions are set for the in-plane strain components, the transverse shear strain, and the normal strain components. An important aspect now is related to the design material, its mechanical properties, the constitutive law, and under a linear elastic material assumption, for example, see the constitutive law introduced for an isotropic material with the well-known 21 elastic constants, or the orthotropic material with the 9 constants, or once again, the laminated composites with a fixed number of laminae within the laminate. And among the class of granular composites, we can also model the so-called functionally graded materials to account for the continuous gradual variation of the mechanical properties of materials from the bottom to the top side of each lamina in order to reduce possible stress concentrations and residual stresses or thermal stresses within the laminates. So this means that the mechanical properties of a functional grading materials refers to those ones of each constituents, for example, ceramic and metal, together with a volume fraction defined according to some fixed continuous laws, as you can see here. And for the cave lamina made of anisotropic material, the constituents in the geometric reference system can be defined as you can see here in this slide, where we determine the transformed elastic coefficients first, and then we can define the generalized internal actions reported on the shell reference surface in terms of the generalized strains by means of the constitutive operator. You can see here as this block matrix, let me say, whose elastic coefficients are evaluated numerically for each point of the reference surface of the shell. And I want now to highlight an important aspect of this approach. I mean, the mechanical properties of each lamina can vary along the three principal directions. So we have this kind of coefficients, and we can consider that the thickness of each lamina can vary along the two principal directions. The fact that the thickness of the shell can be variable. So, but to consider in this model this kind of variation, we have to evaluate the derivatives of the engineering elastic constants in a numerical sense. So I need a numerical technique to do this kind of mathematical operation. So then we apply the Hamilton principle to obtain the equations of motion together with the boundary conditions. We have defined external actions that act on the top and the bottom side of the structure. And after a mathematical manipulation, we get this set of governing equations depending on the inertial quantities together with the boundary conditions of the shell edges with a constant alpha 1 and alpha 2 respectively. And at the same time, if we want to treat a complete shell of revolution as a structural member, we have to satisfy the kinematical and physical compatibility condition at the common meridian, characterized by fixed values of alpha 2, you can see here in this slide, since the shell of revolution represents a special case of a panel of revolution, maintaining the problem completely bidimensional, two-dimensional. And look at these two further examples of shells of revolution, just to show you that similar compatibility conditions can be enforced along the so-called closing parallel or closing meridian. And then we can write the fundamental nucleus in terms of displacement field defined along the reference surface. And then we can assemble the complete system of equations, as you can see here. Now, let's introduce the numerical technique here applied to solve this kind of differential system of equations, so the so-called generalized differential quadrature method, that allows us to approximate the n-further derivative of a function as a weighting linear sum of the functional values at some fixed collocation points by means of these weighting coefficients. So in this context, if we select as basis functions the Lagrange polynomials or the Lagrange trigonometric polynomials or the sinc functions, we have an important mathematical property. I mean, the coefficient matrix A becomes an identity matrix, and the arbitrary derivative will depend on weighting coefficients Dij exactly equal to Aij. So after that, if we want to shift from the definition interval to the physical domain, we have to apply linear transformation of the weighting coefficients between the two different intervals, as you can see here. And if we want to evaluate these weighting coefficients for any derivative order and for any grid of distribution, we can use this kind of recursive formulas proposed in the literature by Xu and others. At the same time, if we want to evaluate integrals of a function. There is another useful numerical tool that can be applied. I mean, the generalized integral quadrature method, as we will apply in the following. And in line with the previous method, the integral of a function in a closed domain can be approximated by a linear combination of the functional values by means of the GIQ weighting coefficients. And these coefficients are evaluated by an inversion of the matrix W that depends on the matrix of the weighted coefficients of the first order derivative computed here. And then if we use this simple relation, we can evaluate the integral of a function in any kind of closed interval. Now, to study a complicated shell geometry, we can start from an unmapped geometry. We introduce a mapping technique to pass through the parent space in order to obtain the distorted geometry. Here is the coordinate transformation where alpha1, alpha2 refer to the physical orthogonal coordinates, and xi eta are the point coordinates in the computational domain. So this requires the use of some blending functions, so where we will use the computer redesign basis function as defined here below by means of the parametric lines of the curvilinear boundaries and the computed corner points of coordinates. And we have to define the Jacobian of the transformation, so we can compute the first order derivatives, and applying the first order derivative definitions 2 times, it's possible to have the second order derivatives. To describe the curvilinear edges of the patch, we use a design tool. I mean, the non-uniform rational B-splines as mapping functions, where a rational curve can be obtained by a projective transformation of the B-splines curves in the projective space. So these functions have some important mathematical properties, as you can see here in this list, that provide a robust description of the problem. So we can study this kind of, any kind of complicated geometries, as you can see here, but I must introduce another important aspect. I mean, the boundary conditions of the curvilinear edges that you can see here in the slide, both in a kinematic and in a static sense. So till now we have discussed about a strong-based formulation of the problem, but another numerical possibility can be represented by the classical finite element formulation. So then for an nth order finite element based on the Lagrangian polynomials, the displacement field can be approximated as you can see here, or in the following compact matrix form. Thus the problem can be written in its variational form. So once again, by applying the Hamilton principle, where the stiffness matrix gets this form that can be rewritten in a discretized form manner using the numerical integration discussed before. And the differential operators defined by means of the Lamy parameters and their derivatives are numerically discretized using the GDQ method. And also for the matrix and the external forces, force vector, we can rewrite then in a discretized form, as you can see here. So, well, now, if we want to treat the dynamic problem of this kind of the structural components, we have to solve a classical eigenvalue problem in a discrete form, where for a static analysis, we have to solve a classical linear problem. So now let's discuss about applications and the results, where we first apply the finite element method based on a strong formulation isogeometric analysis to treat the shell structure components with different shapes. And as first example, we analyze the free vibration of an isotropic panel for different boundary conditions, lamination schemes, higher order formulations and theories, where we can cut the undistorted domain using a rhomboidal shape. And where we show first the accuracy of the numerical method and propose the formulation by comparing the first 10 frequencies for a lamination scheme 30-45 degrees as provided by the first order shear deformation theory and higher order theories against the 3D FEM based approach from commercial codes. So we have used the Abacus in this case. With a very good agreement between results, and here are the related Mohs shapes for the selected boundary condition. As further application, let's consider a cylindrical panel cut by this general shape defined by 2 curvilinear edges and 2 linear ones to yield the complicated geometry you can see here on the right side of the slide, which is made of one isotropic layer, I mean an aluminum, for 2 different boundary conditions, where we compare the 3D FEM-based solutions with the 2D ones as provided by 2D higher order formulations. So the very good matching between results confirms the high accuracy of the proposed numerical approach, despite the reduced computational cost against the classical 3D FEM-based formulation. So as expected, a completely clamped geometry features lower frequency because of the different structure stiffness with respect to the other boundary conditions. So a free clamped boundary condition, where the lowest frequencies are obtained in any case for the same structure with the free edges, as you can see here in the bottom side of the slide, no, because of the increased structure flexibility. Here are the first 6 mode shapes reflecting the selected boundary condition. And for a comparative evaluation between the strong and the weak formulation isogeometric analysis, let's consider a laminated doubly curved shell for different boundary conditions, stacking sequences, higher order formulations, where I cut this undistorted domain using this complicated curvilinear geometry to give the final distorted structures you can see here at the right side of the slide. And here are the results for a completely clamped doubly curved shell structure, where each layer is made of a graphite epoxy material with a stacking sequences 0 plus minus 45 both the strong and the weak formulation get very accurate results compared to the classical 3D FEM elasticity solution. So this proves once again the accuracy of our prediction, which are also plotted in terms of mode shape in line with the selected boundary condition. Now another application involves the doubly curved laminated lattice shell structures as largely used in design, let me say manufacturing, especially in aerospace structures, with different shapes and geometries, of course, depending on their operational requirements. And the mechanical properties of lattice structures are related to their fabrication technologies. So in discrete models, the ribs of the lattice shells are modeled through beam finite elements. Instead, here we apply a GDQ-based continuous model based on an homogenization technique to define the equivalent mechanical parameters. So see here some examples of lattice structure with an isogrid cell or an hexagonal cell, a rectangular cell, or an auxetic cell. So, so for a lattice layer, a first approximation could consider the we can consider the equivalent orthotropic material whose equivalent constants for a unit cell could be computed as a function of the main geometrical and mechanical properties of the ribs. So the accuracy of a GDQ-based continuous model is first checked for a completely clamped rectangular plate with a lattice core by comparing our results in terms of vibration frequencies with respect to a classical FEM approach. So the very good agreement between our results and those ones based on the FEM approach confirm the good performance and accuracy of the proposed numerical method, also for this kind of application. And we also validated the proposed approach considering some analytical predictions available from the literature for two different lattice structures with the clamped edges. So this is the first example you can see here that considers a composite anisogrid lattice cylindrical cell made of two regular system of ribs, I mean the helical and the hoop ribs, with a sufficiently high density, I mean a high number of ribs per unit of length, in line with the continuous treatment of the model, and the comparative evaluation of the natural frequencies is here performed between the GDQ-based equivalent first order shear deformation theory formulation and the finite element analysis proposed in the literature. And you can see here the results for two different lengths where we vary the helical angle phi from 15 degrees to 40 degrees by steps of 5 degrees, and by assuming also different number of helical ribs. So for a fixed length and helical angle phi, you can see has the increased number of helical ribs doesn't lead a significant variation in frequency. But where an increased length of the cylinder from 2 meters to up to 4 meters reduces consistently the vibration frequency for the same values of phi and ns, I mean the number of helical ribs. So the very good also agreement between our results and predictions from the literature confirms the accuracy of the proposed formulation to treat the problem. And this is also confirmed for the further example of completely clamped cylindrical panel or a clamped three-layered doubly curved shell with an internal lattice core made of 4 different ribs families and 2 sheets at the top and the bottom side of the lattice core. And here you can see in this table the results for 2 different sequences of the ribs family of the core with a very good matching between our numerical results according to differential theories. So always based on the application of homogenization techniques, we are also able to analyze orthotropic materials with the honeycomb cell unit that could be used as soft cores within laminated structures. Think, for example, to the graphene, which is composed of a single monolayer of carbon atoms with the honeycomb structures. And look at the successful comparative evaluation of results for a rectangular plate with an hexagonal cell, or I mean the regular honeycomb, between the 3D FEM and the different 2D higher order formulations. And note that the first order shear deformation theory yields accurate results also with a very, very, very limited number of degrees of freedom if compared to the higher computational cost of a classical 3D FEM. So similar considerations could be also repeated exactly for a rectangular plate with a rectangular cell and also for a rectangular plate with an auxetic cell as useful for many engineering applications. So once again, note that the first order shear deformation theory approach combined with the GDQ method is able to provide accurate results, even with a reduced computational cost compared to the 3D FEM approach. So in what follows, if I show you some structural applications of a novel class, let me say of a bio-inspired smart composite materials in which the fiber orientation can vary with continuity within the domain. And in this context, we will describe, so I show you this kind of material, I mean the variable angle toe reinforcement that can be obtained by replacing the reinforcing fibers along some curvilinear paths. So from a mathematical standpoint, the fiber path orientation theta can be written through this law, considering this kind of, you can see here, theta, by means of different parameters. I mean, the fiber orientation along the edge with the alpha 1 and alpha 2 constant, or the fiber orientation in central point of the lamina. And where we are able to consider a variation separately along each coordinate, or a combination of these of both coordinates and variations. So the desired mechanical properties can be reached by combining conveniently these kind of parameters. And here are some examples, so you can see here, of possible curvilinear paths of the reinforcing fibers as obtained with the previous law, by just changing the involved parameters. Now here I show you some results from a parametric study for the vibration response of a single ply conical panel with the variation of the fiber orientation both in the center and along the boundary edges. And here in detail, look at these plots which show a clear variation in percentage, I mean, of the natural frequencies with the variable orientation of the fibers in the central point of the lamina under a selected higher order theory. So note also that the first natural frequencies of the system are even more sensitive to the fiber orientation than the other ones. Whose behavior is also confirmed in these other plots, where we analyze the influence of each natural frequency for a varying orientation of the reinforcing phase along the edge of the lamina. So please look also the different kinematic response, I mean the different mode shape response under the assumption of two different lamination schemes. And where in the color maps, the dark blue, you can see the dark blue color stands for the zero value of the displacement field, and the strong red color refers to the maximum displacement field. So as for example, let's consider a laminated elliptic paraboloid made of 3 layers, where we check for the sensitivity of the vibration response, changing the parameter phi, defining the varying alignment of the fibers, and look at the variation for the first 10 natural frequencies and the selected theory, where we vary the parameter phi. And this reveals the great dependence of the mechanical performance in the structural stiffness just by varying and tuning properly the reinforcing phase and its alignment within the material. And look also the kinematic response, which is perfectly coherent to the selected boundary condition, I mean a completely clamped structure. And an alternative and more general expression can be also introduced to represent the variation of the fiber orientation. So mathematically speaking, this relation can be written by means of 6 different functions, as reported here below. So 6 different functions as the power function, sinusoidal function, exponential function, Gaussian function, and elliptic function, and so on. So here we represent some examples related to the application of this mathematical relation on a square domain. Here are the other examples. And have a look here now, where we represent some examples related to the application. So, I mean, here we have an hyperbolic paraboloid made of 1 layer with a variable mechanical properties, where we focus on the variation of the fiber orientation according to the general law for the first order shear deformation theory. And look at the sensitivity of the response, especially for the first frequencies, when we vary the parameter phi between minus and plus 45 degrees, while assuming a linear and sinusoidal variation of the fiber orientation along the alpha 2 direction. respectively. So, here the response varies when we assume just a linear variation of the fiber orientation along alpha 2 with a clear decrease of each frequency for an increasing value of phi from 0 up to 90 degrees. And as further application, let's consider a clamped free doubly curved sandwich panel of revolution with a foam core and two face sheets with different angle top paths. And here we compare the results from a 3D FEM and results from different 2D higher order theories and different values of phi. So in particular, under the assumption phi equal to 0, the first column here, we revert to a classical laminated composite structures where you can notice the very good agreement between results, and also note also the predictions from different higher order theories are quite close to each other for each value, fixed value of phi. So the same results are also plotted here against phi, just to highlight better the sensitivity of the mechanical response for different distribution paths of the fiber. And let's move to another kind of reinforcing material, I mean functional grading materials and carbon nanotubes in a context where nanostructures are attracting the interest of, as you know, of many scientists. And the proposed formulation allows us to consider the agglomeration of nanostructure embedded in a polymeric matrix and different distributions along a shell thickness, where the volume fraction of the reinforcing carbon nanotube phase is defined, as you can see here below, by means of this quantity VR, which is the carbon nanotube volume fraction value that depends on the carbon nanotube mass fraction and density of both the matrix and the reinforcing phase. And VC instead is defined by different distribution laws throughout the thickness as reported here in this slide. So the overall mechanical properties of the layer reinforced by carbon nanotubes are evaluated using the Mori-Tanaka scheme. So a two-parameter agglomeration model is defined by means of these two quantities, eta and mu, where the first parameter is the volume fraction of the inclusion, I mean the ratio between the volume of the spherical inclusion and the total volume of the lamina. And the second one, eta, is the ratio between carbon nanotubes in the inclusion and the overall carbon nanotubes. So depending on the different relation between these two parameters, we can obtain different agglomerations of carbon nanotubes within the material. And the overall mechanical properties of the composite can be determined in an homogenized form according to the Mori-Tanaka scheme. See, for example, the effective bulk modulus and shear modulus for the composite layer defined by means of the properties of the inclusions and hybrid matrix. And since the composite ply is isotropic, the Young modulus, the Poisson ratio, and the density are evaluated, as you can see here. And where we introduce also these further quantities. And here are some mechanical properties of carbon nanotubes and the polymeric matrix found in the literature. We have referred to our numerical analysis and numerical applications. So now, as numerical application, let's discuss about the free vibration response of a completely clamped shell for different agglomeration parameters of carbon nanotubes. So in this example, we assume a linear distribution of carbon nanotubes along the thickness, where we apply a first order shear deformation theory under a fixed geometry, fixed mechanical properties of the matrix and of the reinforcing phase. So here we plot the first natural frequencies versus the agglomeration parameter eta, where we keep fixed the ratio mu equal to 0.2. And here we analyze the case where mu can be lower or equal to eta, which means that carbon nanotubes can be both included in the inclusions and scattered in the polymer matrix. So each frequency here reported in a rational form with respect to F0, this quantity, I mean the frequency when mu is equal to eta, seems to increase monotonically for an increased value of eta, which corresponds to a varied stiffness, of course, of the material and the structure element. Here we repeat the systematic analysis for a fixed values of eta equal to 0.8, while increasing gradually mu up to the same value of eta. So note the monotonic decrease in behavior for each vibration frequency, which corresponds to a reduction of the structural stiffness because of the agglomeration effect of carbon nanotubes within the matrix. So now as further parametric analysis, we account for the case of a new agglomeration of carbon nanotubes within the matrix. So this corresponds to the case where we assume eta equal to 1, also mu equal to 1, as you can see here, for different values of P. I mean, for different values of the fraction index under a fixed, so under some fixed constants, so I mean ABC, that control the variation profile in each lamina. Here, we note that an increased volume fracture index gets a decreased rational frequency independently of the selected frequency. And as further example, we analyze, for example, the effect of the carbon nanotube agglomeration on the structural response for this kind of doubly curved shell reinforced by carbon nanotubes with a functionally graded variation of the volume fracture throughout the shell thickness, as visible in this plot. And here we just comment about the first natural frequency of the structure versus mu and eta. That seems to be highly affected by the agglomeration of carbon nanotubes, especially for higher values of the mass fraction of carbon nanotubes. So the vibration frequency, in fact, seems to increase for the increased mass fraction of the carbon nanotubes, where we keep fixed both mu and eta. These results can have, of course, a great impact among scientists, especially for optimization design purposes, both for materials and structures. And in this last part of the webinar, I will show you some results from a static analysis for some nanocomposite structural elements, where we want to evaluate the through the thickness strain, stress, and displacement response by means of a recovery procedure in depths. So let's start considering a completely clamped square sandwich plate with a vertical, so under a vertical loading distribution on the top surface. And the sandwich structure has a soft core made of polymer matrix without carbon nanotubes inclusions. Where the external sheets are uniformly reinforced by carbon nanotubes, assuming a fixed mass fraction for a reinforcing phase equal to 0.5. So since mu and eta are equal to 1, the nanoparticles are uniformly distributed in the matrix, and a 4-parameter law is applied now to the carbon nanotube volume fracture in the external sheets to show the influence of the through the thickness distribution of the reinforcing phase. So on the right side of this slide, you can notice the volume fraction distribution of the carbon nanotube reinforcing phase along the thickness of the structure for different values of P, of the exponent P. So note that for P equal to 0, the example reverts to a laminated structures made of carbon nanotube uniformly reinforced layers of equal thickness. And on the other hand, when P tends to infinite, the plate is completely made of polymer matrix. So in this plot, see through the thickness variation of the displacement components and look at the zigzag effect in the kinematic response when P is equal to 0, typical of a laminated structure. And for higher values of P, the structure tends to an isotropic plate, since the soft core effect reduces gradually. So the two limit cases are also obtained by using the 3D FEM model in Strauss in this case, while the intermediate values of P gets a smooth variation in between. So these are the other components and of the displacement, and similar considerations can be also repeated when we analyze the variation of the stress components, I mean in-plane stresses and here, and also out of plane stresses, as you can see here. So this behavior is also reflected in the strain field, as you can here observe in these plots, both for the in-plane strain components and the out-of-plane components. So as a last example, we analyze a clamped, free clamped, doubly curved panel or revolution with a fixed meridian, so made of 3 layers subjected to a normal pressure on the bottom side and to a shear load on the top side. So both the external laminae and the core are reinforced by carbon nanotubes under agglomeration fixed mu is equal to 0.5 and eta is equal to 0.75. So, and the fixed max fraction for the reinforcing phase equal to 0.4. So in this case, also the 4-parameter power law distribution is applied symmetrically to the carbon nanotube volume fraction distribution to describe the true thickness profile of the reinforcing phase, as you can see here. So once again, we compute the displacement, stress, and strain profiles at a fixed point as a function of the exponent P of the carbon nanotube volume fraction distribution at both external layers. And here we don't include the Murakami function in the model since the soft core effect is in this case negligible. Look also the variation of the response, where the case for P equal to 0 corresponds to a structure uniformly reinforced by carbon nanotubes. And here are the other displacement components. And also have a look here for the smooth variation throughout the thickness, also for the stress components, as well as also for the strain field, which is also highly affected in its variation by the selected power values. So of course, this, let me say, this kind of tailorable, this tailorable, response could be of great interest, for optimized design purposes of programmable materials. Of course, just depending on the selected application and the mechanical requirements. Just concluding, so the proposed approach for the analysis of two-dimensional structures by means of the GDQ and let me say also the integral quadrature method has allowed us to analyze anisotropic composite and lattice shells and panels of different shapes, and has allowed us to study also the behavior of generally laminated composite shells and panels characterized by different lamination schemes, and has shown also the influence on the dynamic and static structure behaviors of the choice of a power law distribution for laminates made of functional gradient materials and carbon nanotubes materials, and has provided very close results along with respect to a classical finite element method approach by using different softwares and commercial programs, and also has produced accurate and reliable results for independently of the selected boundary condition and the selected grid distributions. So at the end, I would like to thank you for your attention, and if you have any question, I'm here to reply. Thank you very much.
Okay. Thank you very much, Professor Dimitri, for your nice presentation. We will have time to have some question after the second speaker. So please unshare the screen, and I will start sharing my screen, and we will start. Okay, we will start directly for the other speakers. So the second speaker is Professor Brischetto, Salvatore Brischetto. He is associate professor at Politecnico di Torino. He works in the topic of aerospace engineering. His main research topic are smart composite structures, multi-field problems, hygrothermal stress analysis, carbon nanotubes, inflatable structures, shells 3D and 2D numerical and Excel solution, additive manufacturing, and UAVs. He is author of more than 150 publications, international articles, and he wrote one book, and he is a co-founder and co-chair of the group ASTRA, Additive Manufacturing for Systems and Structures in Aerospace, and also founder and chair of the project Polydrone, a multi-purpose modular drone produced via 3D printing. So now we can skip directly to the presentation entitled 3D and Advanced Shell Model for the Analysis of Single and Double-Walled Carbon Nanotubes and Nano-Reinforced Structures. Please, Professor Brischetto, share your screen.
Okay.
You can start.
Thank you for your introduction, Professor Tornabene. So the title of my presentation is Three-Dimensional and Advanced Shell Models employed for the analysis of carbon nanotubes, both single and multi-walled carbon nanotubes, and nano-reinforced structures, in particular plate and the shell geometries. So this is a brief summary of the presentation. First of all, some important remarks about the meaning of three-dimensional, two-dimensional, and one-dimensional structural models. Then an overview on single-walled and double-walled carbon nanotubes. Then we speak about the nano-reinforced composite plates and shells. So we'll see several types of nano-reinforcements. The fourth section is about the main results, about the free vibration analysis of single-walled carbon nanotubes and double-walled carbon nanotubes. And then some static analysis about composite plates and shells where several nano-reinforcements are included. Then the main conclusions about the proposed results. So first part, the meaning of three-dimensional, two-dimensional, and one-dimensional structural models. In general, in the real life, a problem is three-dimensional. A three-dimensional problem means that, for example, if we have a displacement formulation, the displacement components are functions of the three coordinates in the space, x, y, and z. And if I solve a three-dimensional problem, I work with unknown vectors, I work with variables which are functions of x, y, and z. If I pass to a two-dimensional problem, in this case, the variables, the displacements, in the case of a displacement formulations, the variables are functions of only two coordinates, x and y, because the z coordinate dependence is transferred to an opportune thickness functions. Finally, if I have a one-dimensional problem, in this case, the variables, the unknowns, the displacements, in the case of displacement formulations, are functions of only z coordinate. The dependence on the other two coordinates is transferred to appropriate functions. So this is the meaning of to perform three-dimensional, two-dimensional, and one-dimensional analysis. In details, in the case of three-dimensional problems, we have as typical structures squat solids, because in this case the three dimension A, B, and C have the same importance, and no dimensions are negligible. So I work with a displacement component, with a variable which is function of the free coordinates. In the case of two-dimensional problems, we have the typical bidimensional structures. Typical bidimensional structures are, for example, plates and shells. And in this case, a dimension, in particular the dimension through the z direction, which means the thickness dimension, is negligible with respect to the other two dimensions in the plane. So this is a typical bidimensional structure. This is a plate where we have no curvature in the in plane directions. And in this case, we can transfer the thickness coordinate in opportune thickness functions. In the case of curvature, we have shell structures. This is some examples, for example, cylindrical panels or spherical panels, when we have only one curvature in the alpha direction, or we have two curvatures in the two alpha and beta directions. So we can write this formulation in both rectilinear orthogonal coordinates or in rectilinear orthogonal curvilinear mixed coordinates. Finally, in the case of one-dimensional problems, we have two dimensions that are the typical dimension in the cross-section of the structure. These two dimensions are negligible with respect to the main direction. This is that is L, the longitudinal direction, in the Z direction. So in this case, we can transfer the dependence on the two coordinates where the dimensions are negligible in opportune functions, and our variables are functions of only Z coordinate. In summary, when we have structural mechanic analysis, we can conduct this analysis by means of three-dimensional solid, two-dimensional plates and shells, and one-dimensional rods and beams elements. So we have functions that depend on x, y, and z, or only on x and y, or only from z. This feature means that the simplest element is the one-dimensional one, while the most complex is the three-dimensional one. Then these equations must be solved. So we can solve it by means, for example, exact solutions, in order so we obtain typical closed form solutions, or we can use numerical solutions. Some examples are finite element method or the generalized differential quadrant method, as explained by Professor Dimitri. The exact solutions are valid only for particular materials, particular lamination schemes, particular geometry, and particular load and boundary conditions. So these exact solutions are very important because they do not have numerical problems, but they are not general. Okay, they are valid only for particular cases. Okay, but they are very important because we can use them to validate the related numerical solutions. Numerical solutions are possible for several cases. So we can consider several different materials, geometry, load, and boundary conditions. Obviously, in general, numerical solutions could be less accurate than the related exact solutions because, for example, we can have several numerical problems. And these numerical problems sometimes are hard to be solved and to be interpreted. But in the engineering applications, numerical solutions are the only ones that are used because they are general and they have a wide range of applications. The exact solutions are only used for comparisons reasons and in order to validate the related numerical models. So this is the main introduction about the idea of a three-dimensional, a two-dimensional, and a one-dimensional modelization. Now we can see further details about these aspects. First of all, we can see a general exact three-dimensional shell model. This general exact three-dimensional shell model is written in orthogonal curvilinear mixed coordinates. So two coordinates, alpha and beta, are curvilinear in the plane. The other one is always rectilinear, the z coordinate in the thickness. And this model is general because we can write the equations for double curved shells. In particular, if we want to obtain exact solution, these double curved shells are only the spherical shells, because we need to have the two radius of curvature equal between them in order to simplify some terms and in order to obtain closed form solutions. But in spite of this, this is an exact solution. This is general because we have equations for spherical shells, and then these equations they generate in those for cylindrical shell panels, cylinders, and plates. First of all, in case of curvilinear coordinates, the length of the edge of this fundamental element are not rectilinear. So we have some terms which depend on the z coordinate and on the radius of curvature. And the same idea is valid for the fundamental element area and for the fundamental element volume. Okay, so we have these two terms, the parametric coefficients, which consider the effect of curvature depending on z coordinate. If you note these last equations, obviously z coordinate is rectilinear and the relative parametric coefficient is equal to 1. Okay, so we write the geometrical relation for spherical shells. Spherical shells in this case have these two radius of curvature which are equal between them. So this is a great simplification, and it allows us to write very simple geometrical relations which links the strain components with the displacement components, and these are the geometrical relation for spherical shells. Geometrical relations for cylindrical shells can be obtained by considering one of the two radius of curvature as infinite, so the related parametric coefficient is equal to 1. And in this way, these equations are simplified in these equations. These are the geometrical relations for cylindrical shells. In this case, we have considered infinite R beta radius of curvature and the related parametric coefficients H beta is equal to 1. So these equations are simpler than the previous one. Moreover, if we also consider the other radius of curvature as infinite and the related parametric coefficients as equal to 1, we have the typical geometrical relations for plates. These are well known. If we want, we can also call in this case H and beta as x and y as rectilinear coordinates. Okay, so these are the geometrical relations for plates. Similar considerations are also valid for three-dimensional equilibrium equations. So these are the the three-dimensional equilibrium equations written for spherical shells. Okay, obviously with the simplified hypothesis that both the radius of curvature are equal. And then from these equations, we can obtain the equations for cylindrical shells and for plates. This is important because in our MATLAB in-house software code, we implement only these equations. The equations, the geometrical relations, and the three-dimensional equilibrium equations for spherical shells. And the other geometries, cylinders, cylindrical shell panels, and plates are obtained as particular cases. Okay. In this equation, we can see the typical derivatives, partial derivatives of stress components, three-dimensional stress components, typical of three-dimensional equilibrium equations. And we can also have the inertial terms, okay, where we have the second temporal derivative of the free displacement components. Obviously, we write these equations for each K layer. Okay, so we have a multi-layered structures, and these equations can be written for each K layer. So this upper script means the particular K layer. Then these equations can be simplified for cylindrical shells by considering infinite R beta radius of curvature and the parametric coefficients H beta equal 1. And then considering also the other radius of curvature is infinite, we have the typical three-dimensional equilibrium equations for flat plates, as you seen in all studies, papers, and so on. Now, the second step is to consider the generalized Hooke law. So we have the Hooke law for the three-dimensional case, written for each K layer, okay? And then in order, I recall that we want to obtain closed form solutions. In order to obtain closed form solutions, we consider harmonic forms for the free displacement components, okay? And this also means that all the edges of the structure are simply supported. And in this case, we have the index J in place of the index K only because we have divided each physical layer in several mathematical layers in order to calculate the parametric coefficients H alpha and H beta, because these equations have not constant coefficients. They have not constant coefficients because there are the dependence on Z coordinate. So we eliminate this dependence on Z coordinate by introducing several fixed mathematical layers. So after all the substitution, we obtain this final system, okay? This final system depends on J mathematical layers because in general, for each K physical layer, these coefficients are not constant because we have the dependence on the thickness coordinates and the curvature effects. But for example, if we also consider functional graded materials, the elastic coefficients depend on Z. So in general, these coefficients are not constant. But we need to have a system of partial differential equations Z with constant coefficients if we want to solve it. So we introduce several, we divided each K physical layer in several mathematical layers, and we can have constant coefficient equations. This system of free-order differential equations are a system of second-order differential equations Z. In fact, we can note that some displacement components have the second derivative performed with respect to Z coordinate. These 19 terms are very, very complicated because they have inside several geometrical and material informations. And obviously, these partial differential equations are written for spherical shells, and they automatically degenerate in those for cylindrical shell panels and plates. In order to solve this equation, first of all, we reduce the order of the derivatives, so we obtain a system of first-order differential equations, and this is obtained by redoubling the number of variables. So, in the previous system, we have three unknowns, which are the free displacement components. But if we also add as unknowns the derivatives performed with respect to Z of the free displacement component, okay, we reduce the order of the derivatives. So we have a system of first order differential equation Z. This is very important. Moreover, the fact that these free derivatives are obtained directly from the model is very important, because in this way we obtain very accurate derivatives in Z. This is as a sort of mixed models, because in general, when we obtain the stresses, the problem of stresses is to correctly calculate the derivatives in Z to obtain correct strain values to substitute in the causative equations. But if these derivatives are correctly calculated, the results in terms of stresses improve. In order to solve this system of partial differential equation Z, we use the well-known exponential matrix method with an opportune expansion in Z. And finally, the last condition is, if you remember that the equations are written for each layer, and we use a layer-wise approach, which means that we write the equations for each separately for each layer, okay? And then we need to collect each layer between them, okay? We have the problem at each interface in order to impose the continuity conditions, okay? Because we use a layer-wise approach. This is important because thanks to the layer-wise approach, we can obtain very refined results, okay? How to impose these interlaminar conditions? We impose these interlaminar conditions in terms of displacement components. This means that each displacement component is continuous at the interface. The bottom value for the J layer is equal to the top value for the J minus 1 layer, and so on. And these are the typical congruency conditions. Then we impose also the equilibrium conditions for the transverse shear and transverse normal stresses. This is the same. The stress component at the bottom of the J layer is equal to the top value for the J-1 layer, okay, for the previous layer. Okay. After this, we have a layerless model, but this layerless model is very, very important. One consideration. It is not very heavy from the computational point of view, because even if we use a layerless approach, first of all, the convergence of this this expansion is very, very fast, and moreover, even if we use a layerless approach and we impose the continuity by means of these transverse matrices, finally, we obtain always a final matrix which is always 6 by 6, independently by the order of expansion for the exponential matrix method and the employed number of mathematical layers. Okay, so if we want to solve a static analysis problem, we have this typical linear elastic problem. So we have the matrix for the unknown vector and equal to the applied loads. We can have a load applied at the top and at the bottom in transverse shear and transverse normal directions. For a typical free vibration analysis, we have a typical eigenvalue problem. Okay, so we must calculate the determinant of the matrix A. Okay, now in the results, in the proposed results, we also we'll see some two-dimensional models, okay, and also some one-dimensional models. So in a very brief way, we can see some data about the two-dimensional models. First of all, the well-known, the most famous two-dimensional model is the plate model based on Kirchhoff hypothesis. When these Kirchhoff hypotheses are extended to multilayered structures, we have the typical classical lamination theory. In this model, we have only 3 degrees of freedom because the rotations are written in terms of derivatives of the W0 displacement. A first refinement of this model is, for example, the Reissner-Midland hypothesis. This hypothesis, extended to multilayered structures, gives the so-called first-order shear deformation theory. So we introduce the transverse shear strains, and we have 5 degrees of freedom. The 3 displacement components in the middle surface and the 2 rotations. Then we have several refinements of these models. These are some examples. For example, second order theory with the transverse inextensibility. So we have 7 degrees of freedom, or the well-known Vlasov-Reddy theory, where we have a cubic term in U and V, and we have only 5 degrees of freedom, okay? Obviously, all these theories have constant transverse normal displacement. And this is a problem because in this way, we discard the transverse normal strain, okay? And for example, for some problems, for example, very thick plates, this is a problem, a great approximation. Moreover, these models have some problems for example, the Poisson locking problem. We solve this problem by means of the use of reduced elastic coefficients and so on. Then there is another family of higher order theories. Professor Dimitri spoke about this. So for example, in equivalent single layer approach, which means that we consider all the multi-layer structures as one equivalent structure. So the expansion for all the displacement components is written for all the multi-layer structures. In this notation, you cannot see the dependence on the K layer, which means that we write the expansion for each separated layer. So in this case, we improve the results, for example, for very thick structures, because we introduce the thickness stretching effect. But we can have some problems, for example, for structures which have an high transverse anisotropy, because in this way we cannot obtain the typical zigzag effect. Okay, the zigzag effect can be introduced in an artificial way. For example, we have the typical kinematic-based zigzag theories that they are very simple because we add a function, a very simple function in order to recover this zigzag behavior. Or we have the so-called physically based zigzag theories. Okay, these are more complicated, but they are more general. They have a wide range of applications. So the kinematic-based zigzag theories are simple, but they can have some problem for particular lamination schemes, particular load conditions, or particular boundary conditions. Physically based zigzag theories are more complicated to implement, but they have a wide range of applications. If we want to introduce the zigzag effect without these points, 1 or 2, we can use the so-called layerless theories. So the expansion is written for each K physical layer. Okay, so we have a displacement approximation for each K mathematical layer. These higher order theories are, for example, typical in works by Carrera and these co-authors. So, what are the steps to obtain two-dimensional displacement models? First of all, step 1, opportune variational statement. We chose the opportune variational statement. In the case of a displacement formulation, we have the typical principle of virtual displacements. Then we have the substitution of the appropriate constitutive equations, the substitution of the appropriate geometrical relation for plates, for shells, and so on, and then the substitution of the appropriate kinematic model, Kirchhoff, Rice-Middlin, and so on. Then the final equations can be solved or in an analytical way or by means of an analytical model. In the case of analytical solutions, we have the substitution of harmonic variables, and then we have the integration by parts to obtain the closed form solution. In the case of numerical solutions, we have the typical, for example, the typical method is the finite element method. So we have the shape functions in order to perform the derivatives in a numerical way in the two in-plane directions. And we have the other concepts such as mesh, nodes, degrees of freedom, and so on. Obviously, finite element solution is only a possibility. There are several types of numerical models. The GDQ is another possibility, and so on. This is only a recall to see that, for example, if we have affiliated structures, we write the rigidity metrics for each layer, and then in an equivalent single layer approach, these stiffness metrics are summed. Okay, so we cannot consider each layer separately, and we cannot consider the typical zigzag effect. In the case of a layerless approach, we write separately the stiffness of each layer, and then we have the typical layerless assembling. Okay, the typical layerless assembling that is here and here, we impose the typical continuity conditions, interlaminar continuity conditions. Okay, obviously there are also the one-dimensional problems. An example is the Eulero-Bernoulli beam theory. There is a strong analogy with the Kirchhoff plate model. It is obvious because we discard the typical shear effects, so the normals remain perpendicular to the middle surface. Another possibility is the Timoshenko beam theory. There is a strong analogy with the Rice-Middlin plate model. So in this case, we introduce the shear effects. Okay, so the rotation is not the derivatives of the in-plane displacement because we have the gamma xz strain. Okay, and in analogy with the plate models, we can have some refinement of this theory. This is a typical example. For example, the models by Bartzuman, Reddy, Turatier, and so on. Obviously, beam models can be solved in both numerical and analytical way. Now we can see some details about nanostructure. Obviously, we have nanostructured materials when we are in a range from 1 to 100 nanometers. These materials have remarkable mechanical, electrical, optical, magnetic, and thermal properties. Are very important carbon-based nanomaterials because they have very important mechanical properties. So this is a typical example of nanotube discovered in Japan in 1991, and the length to diameter ratio can go to a very, very big value. And we can see this carbon nanotube as a single sheet of graphite made up of carbon atoms, arranged in a honeycomb lattice and rolled on itself. Depending on the axis of rolled, we have different nanotubes types. with the different properties. So we define the chiral vector, okay, CH, with these two unit vectors, and this number m and n are integers. So depending on the angle theta between the chiral vector and the unit vector A1, we have different nanotube types. So when m is different from 0 and n is equal to 0, we have the typical zigzag nanotubes. So theta is equal 0. Then when we have a general, when m is equal n, we have the typical chiral nanotube, and then we have the armature nanotube. Okay. So the armature is when m is equal n. Okay. So the chiral vector gives the circumference of the circular cross-section of carbon nanotube, and the longitudinal axis of nanotube is perpendicular to the chiral vector. And depending on this longitudinal axis, we have different geometries with different properties. Okay, this is a typical example for an armature where m is equal n, or chiral where m is different from n. So we can see the difference of the longitudinal axis used to roll the sheet. Okay, and depending on these properties, chiral, armature, zigzag, we have, for example, conducting nanotube, other with similar metallic behavior, and so on. Then another possibility is single-walled carbon nanotubes and multi-walled carbon nanotubes. In the case of multi-walled carbon nanotubes, each single nanotube is linked with the other by means of the van der Waals forces. Okay, so this is a way to consider the van der Waals forces by means of the coefficient of interaction C and the deflection jump due to deformation. Okay, and in our models, in our Livers models, we must think how to introduce this van der Waals force, because we cannot use the typical interlaminar continuity conditions. Okay, so this is a recall about the important properties in terms of mechanical, optical, electrical, and thermal properties for carbon nanotubes. They can have elastic modulus from 1 to 5 terapascal and a very low density. So the specific properties, that is the elastic property divided the mass density, are very high values. How to consider the mechanical modeling of carbon nanotubes? We can consider a molecular dynamic models where we solve the Newton equations of motion for a system composed of a certain number of atoms, and we solve the equations of motion in very small time steps. This is the first approach. The second approach is an atomistic-based models, finite element models, where we have the beam elements in order to describe the interatomic covalent forces, and the concentrated masses which represent the carbon positions. We have some problems to solve in this method because we must decide the rigidity of the beam elements in order to describe the interatomic covalent forces, and we have an high computational effort. A third possibility is an equivalent continuum models, because carbon nanotube is a discrete model, and we consider an equivalent continuum tube where we suppose an hypothetic thickness. Obviously, the problem here is to define opportunity, the Young modulus, the Poisson ratio, and the wall thickness H. There are several possibilities in the literature in order to solve this problem, and that is atomistic approach versus continuum approach. So in order to obtain a Young modulus, which could be quite correct, we must define this hypothetic thickness, and it is not so easy. One of the possibilities is to solve the Tersov-Brenner potential, in order where we link the stiffness bending with the in-plane rigidity, and we consider also this limit. Okay, this is limit H minus 0.142 nanometers is for equilibrium conditions, and then from all this system of equations we obtain opportune values for the Young modulus and the equivalent thickness. In the case of double-walled carbon nanotubes, there is the same problem, so we must define a first thickness for the first concentric carbon nanotube and an opportune thickness for the other concentric nanotubes. And after this, in case of equivalent silicon layer approach, we can consider a carbon nanotube, a double-walled carbon nanotube, as only one carbon nanotube with the total thickness 0.7. In the case of a layer-wise approach, we cannot consider this type of assembling because they are not multilayered structures with interlaminar continuity conditions, but they are separated. But if they are separated, the two nanotubes are not linked between them. We must introduce the van der Waals forces in order to collect the rigidity of the two single-walled carbon nanotube. So the idea is to include the van der Waals forces in the layer-wise approach. This is the typical equations that we have seen. And these equations, a first possibility, gives these two forces, which means to add to our assembling in this way by adding these terms. So in this way, the red block and the blue block are connected between them. Okay. Another possibility, a second possibility, is to introduce as a fixus layer, a very thin fixus layers, which represent the van der Waals interactions. So the two nanotubes are separated, are very, very close between them, and they are separated with this fixus layer, which represent the van der Waals interactions. So in order to calculate the properties of these, the elastic properties of these fixus layers, we start from the van der Waals interaction coefficient, and then we arrive to opportune values of Young modulus to give to this layer. Another block is the third block about the nano reinforcement of composite plates and shells. So there are several possibilities. We can see some of them. For example, carbon nanotubes embedded in thermoplastic and elastomeric polymers. In the case of curved carbon nanotubes, we improve the elastic properties. So there is an example. For example, for a volume fraction equal 3%, we have the comparison between single-walled carbon nanotubes which are rectilinear and those which, no, in this case are both rectilinear. The first one is rectilinear, the other one are single-walled or double-walled with an opportune curvature. But we can see that if there is no adherence between the carbon nanotubes and the matrix, the properties do not improve with respect to the original polymer. We need the adherence, okay? And we can see the difference between a rectilinear carbon nanotube and the other types, okay? These are other similar results in this sense. So we have a comparison between single-walled carbon nanotubes reinforcement and double-walled carbon nanotube reinforcement with the adherence and with different volume fractions. Another possibility is we have a matrix and we have the typical fiber, rectilinear fiber reinforcement. So we can add some carbon nanotubes on these fibers in order to improve the adherence between the matrix and the carbon fibers. Okay, and there are several possibilities to add these nanotubes as reinforcement. Okay, these are nanotubes added to the single fiber, allow to improve the adherence between the matrix and the fiber. So, for example, we can see as these are the 4 cases explained in the feature, and these are the example of the multi-layered composite structure without carbon nanotubes. When we add the carbon nanotubes in each single fiber, we improve in particular the transverse normal Young modulus. Okay. Another possibility is the silicon foam. We have sandwich structures with a silicon foam core, and this silicon foam core can be reinforced by means of carbon nanotubes. But in this case, and we can see as when we add a percentage, a different percentage weight of carbon nanotubes, the mass density increases very, very slow, while the Young modulus has a very big incrementation. Okay. Obviously, another last possibility is the use of clay reinforcement in polymeric matrix. In this case, in order to calculate the equivalent Young modulus, we can use the Mori-Tanaka scheme or the strain gradient Mori-Tanaka scheme. And it is important to use the strain gradient Mori-Tanaka scheme because when we have very small reinforcement, we have some strain gradient at the interfaces between the matrix and the reinforcement, and we must consider this effect in order to obtain the correct values. So we can see the difference when the percentage of clays increase. This is the Young modulus obtained by means of Mori-Tanaka scheme, and this is obtained by means of strain gradient Mori-Tanaka scheme. Okay. So some results, in this case, we compare a beam model with some shell models. And this is only, this is a double-walled carbon nanotubes analyzed by means of equivalent single-layer approach. Obviously, there is a difference between beam model and shell model when the carbon nanotube is short. This difference is smaller when the carbon nanotube is long. Another possibility is to include the layer-wise approach. So in this case, we have the van der Waals forces, okay? And the results are completely different with respect to the equivalent single-layer approach. In this case, we can see the difference between the equivalent single-layer approach and the layer-wise approach with the van der Waals interactions. So the differences increases when the order of frequencies increases, and it is bigger for the short carbon nanotubes. Other results are obtained with the traditional model, and this is important because with the beam models, we can have results for moderately long and long carbon nanotubes, but when the carbon nanotubes are very, very short, we need a three-dimensional shell model. So we have performed several results about several chiral vectors, so for armature, zigzag, and chiral nanotubes. These are not so important. We can see the different properties in terms of frequencies depending on the chiral vector and depending on the type of carbon nanotube. So the first, second, third mode, and so on. Another important consideration is to consider the difference between the three-dimensional model when you include the van der Waals interaction, so a layer-wise model with the van der Waals interaction, or a layer-wise model without van der Waals interaction, only with the interlaminar continuity conditions. And this is a very big difference because for short carbon nanotube, this is the difference in percentage between the results, for the results obtained between a three-dimensional model where the layer-wise approach is obtained by means of interlaminar continuity, okay? And in the other case, the two carbon nanotubes are linked by means of the van der Waals interactions. So there is an important difference. Okay, similar results. So can go. So we can see here the van der Waals effects increase with the order of frequency, and it is more important for short double-walled carbon nanotubes. These are other similar results for carbon nanotubes and the comparison with the GDQ model by Professor Tornabene. And we can see the difference between a three-dimensional shell model and two-dimensional shell models and beam and the related beam models. So we have several results of this type. And also in this case, we can see the difference between a three-dimensional exact shell models in layer-wise approach, where the two carbon nanotubes are linked by means of interlaminar continuity conditions, and the case where the two carbon nanotubes are linked by means of the van der Waals interaction forces. So these are all these typical results. Then we can see some results about reinforced plates and shells. In this case, it is very, very important to use a higher order models, for example, layer-wise approach, because when the plate is thick, when we have sandwich configuration with a high transverse anisotropy, the classical lamination theory and the first order shear deformation theory do not work, okay? Because, for example, we can see here this, okay. For example, if we want to obtain the correct value for the transverse normal stress, we need a higher order model. We cannot use the classical lamination theory or the first order shear deformation theory, okay. So this is a typical example can be found here. This is the typical zigzag form of transverse normal displacement in the case of a sandwich structure. Okay, and this behavior can be obtained only by means of a layer-wise refined model. Then in these images, you also found the effects of carbon nanotubes. When you add a percentage weight of carbon nanotubes, the structure is more rigid and we obtain smaller values for transverse normal displacement. Okay. Here it is important because we can see the transverse normal displacement obtained by means of a refined shell model. And in this case, we have introduced the elastic property calculated by means of the Mori-Tanaka scheme and the elastic properties calculated by means of the strain graded Mori-Tanaka scheme. So we can see a bigger difference in terms of results, in particular when the percentage weight of clays increase. This difference increases exponentially, okay? So these are other similar results to compare refined models with the classical models. In this case, another important consideration can be found here, so we can conclude because the time is not is finished. So the last thing, important thing, can be here. So we can have the effect in terms of transverse displacement when the percentage of carbon nanotube increase. And here, so these are typical results. And here, where is it? We can see this important aspect. In this case, we have calculated the transverse displacement for our layered shells when the matrix is reinforced with a percentage in weight of clay, 5%, 7%, 9%, 12%, and so on. And we can see as the transverse displacement obtained with the shell model when the elastic properties, the equivalent elastic properties, are calculated by the strain gradient Mori-Tanaka scheme, are very, very similar to the transverse displacement obtained when the elastic properties are obtained experimentally. Okay, so we can see as the experimental values for the elastic properties are very, very close to the elastic properties obtained by means of the strain gradient Mori-Tanaka scheme. If you include the transverse displacement obtained with the elastic properties obtained by means of Mori-Tanaka scheme, there are larger differences. So, in conclusions, we have seen the importance of defining the correct equivalent elastic properties for carbon nanotubes when they must be analyzed by means of structural elastic models. We have seen the importance of shell models for the analysis of short carbon nanotubes. We have seen the difference between a layerless approach and equivalent single layer approaches in the case of double-walled carbon nanotubes analysis, and in this case we also seen the effects of the van der Waals forces. Then we have seen also the importance of correctly evaluating the improvement of elastic properties when nano reinforcements are added in plate and shell structures. And finally, we have seen the importance of using refined two-dimensional shell models or three-dimensional shell models when we want to analyze thick and moderately thick nano-reinforced plates and shells, because we have several effects: the thickness effects, the in-plane anisotropy effect, and the transverse anisotropy effect. Okay, thank you for your attention, and I have finished. Thank you so much.
Thank you very much for your nice presentation, Professor Brischetto. So I will start with Professor Dimitri. And so the first question is, when you talk about VAT for the first time, you have shown a picture with some plants. I would like to know which is the connection.
I just show you this picture with this connection with plants because it was related to a sort of bio-inspired design. I mean, to natural composites, no? Such as the carnivorous plants we have seen in the slide, because they evolve some hierarchical architectures, displaying a remarkable fast adaptation, let me say, in response to environmental stimuli. So based on this bio-inspiration, we can think to develop some programmable materials whose microstructures can be designed for specialized functionalities. And so just by tuning properly the curvilinear distribution and orientation of the reinforcement phase. So just to have this connection between so nature and applications, so applications and theory.
Yes, okay, so we have some special cases in nature, and so we can copy from...
yeah.
Yes, yes. And a second question is, with the proposed numerical formulation, are you able to capture nanoscale effect within nanostructures?
Yes, basically yes, but I must combine the proposed numerical approach, I mean the generalized differential quadrature method, with some non-local continuums theory to account for small scale effects and for depending on the selected nanostructure. So, for example, in this direction, recently we have we have applied in some works published in Nanomaterials and Composite Structures, some works where we have applied this numerical method, so the GDQ method, within some non-local strain gradient theory. So to study, for example, anisotropic nanostructures, so nanobeams or nanoplates and nanoshells. So also in complicated couple conditions, so let me say, not only to study the mechanical properties, but also for some more complicated coupled thermomagneto and piezo mechanical conditions. So
very nice and important aspect. Thank you. Thank you very much for your nice presentation, and thank you very much for answer the questions. And so we will skip directly to the second speakers. And Professor Brischetto, I have two questions for you. And the first one is, how did you impose the interlaminar continuity condition in the 3D shells model?
Okay, it is imposed by means of opportune transverse matrix. In this transverse matrix, you impose the continuity conditions in terms of displacements and the continuity conditions in terms of transverse normal stresses. And then we have matrix products. And these matrix products performed by means of transfer matrix allow us to remain with a 6x6 final matrix. Obviously, in this case, there is a problem with respect to two-dimensional shell models. There is a problem when you must include the van der Waals interactions. So if you have seen, there is a difference between the two methods. In the first case, you are able to include directly the van der Waals forces. In the second case, you must use a fixture layer which represents the van der Waals forces.
Okay, thank you very much. And the second question is, the two methods in layer-wise approaches to include the van der Waals interaction in the doubly curved nanotubes are coincident in terms of final results?
Yeah.
Values and so on.
They are quite similar. Okay, there are not very big differences. If you include direct the van der Waals forces by means of the coefficient C, so you put the coefficient C in an opportune position in your multi-layer matrix, or if you use the fixus layer where you use opportune values for the Young modulus derived from the coefficient C, the two methods in terms of frequency results are very, very close between them.
Okay, so I want to thank you very much to the two speakers, and now I want to share the screen because I want to highlight something for the next. So we have another seminar, another webinar. I want to go advertisement for all the participants regarding this webinar. So in the next October 30, we have other two speakers, in particular Professor Carola Esposito Corcione and Professor Victor Emeriev. So this is an advertisement for all the participants. I want to thanks again to MDPI company to give me and to give to the two speakers presented here today to give us the possibility to present our important topic and research. And so I will give the talk to Elena in order to close this webinar. Thank you very much for your attention. I stop sharing my screen now.
So thank you, everyone. I would like, before going, thanking again Dr. Francesco Tornabene, Dr. Salvatore Brischetto, and Dr. Rossana Dimitri for this amazing talk and the amazing webinars. And I have shared some information on the chat for you to register to the next Nanomaterials webinar, and if you want to stay updated on upcoming webinars from Nanomaterials as well. And remember that certificates of attendance will be available on demand. As we didn't have many questions now, I think there's one question. I don't know if
there is another
yes.
question. I want to.
You can answer it, maybe.
Yes, from Sami Abu Sali. It's for the second speaker, Professor Brischetto. Is van der Waals force depend on the force and on displacements?
Van der Waals forces depend on the displacement, and when we add it in the multilayer matrix, in fact, we put the coefficients in the right position, and then we have the related displacement, which are unknown vectors in the vectors of displacements. So it is correct. It's right.
Okay. So thank you very much again for you, and thank you very much, Elena, for have the patience to to organize this webinar. And so thank you very much, all the participants, to be here, and see you in the next webinar on October 30.
Goodbye and take care,
Bye.
all of you. Thank you very much.
Take care to all of you.
Bye, everyone.
Have a nice day.
Bye-bye.
Bye. Have a nice day.